So I think with that, we can hand over to the main event, which is Andrew and Adam.
Awesome. Thanks very much. So I think before we share our screen, Adam and I will chat a little bit, sort of give you a broad overview of the motivation for this, sort of where it comes from, and then the bulk of what we'll do is just sort of show it off and get people to play. What I might do is I might post a link to the website in the chat so that if you're bored with us talking at any point, you can then just go to the website. Adam, if you want to give your thoughts that you mentioned to me Monday, maybe that's a good start.
Yeah, sure. So something we've been thinking about quite a lot when we teach our courses here in Durham. So Andrew and I have been teaching a mathematical biology class together for a few years. It's a third year course, but we also do tutorials for first and second year courses. Something we've been thinking quite a lot about is which tools do students use? Which ones are they familiar with? If we ask them to do something like plot a graph, and in fact, having just marked a lot of papers where we asked them to plot a graph and that went interestingly, it's interesting to think about what tools do students use, and then do we know that they have those tools, or do we know how to use them? So I thought I might start by asking you this question, and if you can throw your thoughts in the chat. If we ask students to, here's a function, what does it look like? Or if I asked you, here's a function, what would it look like? Can you type in the chat what you would use to try to answer that problem? So I'll let you head over to the chat and just throw some things out there. Right, MATLAB, strong contender, right? Yep. Wolfram Alpha, yep, I agree. Wolfram. We've got Maple coming in, right? We found the Canadian. Yeah, right. Found the. So Mathematica. This is okay. Yeah, please keep on throwing these in. Desmos for low level, right? GeoGebra. So this is Cheb Fun. There's always one. So this is sort of the answer that I would expect from I was about to say our generation, but effectively, staff that are already working in universities, right? So I think, MATLAB or Python, if you've got it set up, it's a very easy tool, right? You just type it in, you know what you're doing. It's a much more extensible piece of software. Wolfram Alpha, I would be surprised if any of our any of our students use Wolfram Alpha, but when I was an undergraduate, that was massive, right? Using Wolfram Alpha to invert like a 4x4 matrix, and it showed you all the steps, was really helpful in linear algebra homework. Mathematica, again, really great tool once you know how to use it. Colin points out, some students might follow an algorithm about stationary points. This is assuming that they might actually draw it themselves. Desmos is the one rightly pointed out here as being the one that I think nearly all of our students would know how to use. This is a online plotting tool that seems to have really good coverage over all of our incoming A-level students, who did their A-level and then came in. And I was watching the I don't know if any of you watched the Apple keynote earlier this week. So on Monday evening, Apple was announcing sort of some new software that they were having, or that they're putting out. And they finally released a calculator for the iPad, which gave great news. But one feature of this, and they were sort of showing off some of their AI stuff, is that you can now on the Notes app, or you will be able to on the Notes app on your iPad, write down some equation, y equals some function of x. Write it down in your handwriting. You can have parameters in there that you name somewhere else. And you can just get it to insert the graph of that function. And then you can just change the value of the parameters on some sliders, right? You should check out the keynote if you haven't seen it. It's really cool. And the graph's going to change. This is software that our students are just going to have, just as part of their normal, the most basic tools on their iPads and on their computers. And so when we are talking about VisualPDE, so we're solving sort of higher level problems, but what we're trying to do is we're trying to hook into this idea that our students use tools as faculty, very few of us actually use them or know about them. Andrew and I reckon that maybe 35% of our colleagues here even know what Desmos is. And so what we're hoping is that when we'll let you play with VisualPDE and show you some stuff, is that we're going to be giving our students a space to play in the same way that they can play with solving or plotting equations in things like Desmos. You're trying to use their intuition for these online tools to solve higher level problems, and in this case, trying to solve or looking at solutions to partial differential equations. Andrew.
Yes, thanks very much. So indeed, part of the motivation here was sort of twofold. So some of it is really give them this ability to play, give them this interactivity, which I'll show you in a moment, but also importantly to convince our colleagues that they should keep up with this stuff, because PDEs have a history of being extremely technical, extremely hard to solve. Tremendous amounts of the supercomputing revolution in the 80s to the early 2000s was motivated by solving equations of physics on massive supercomputers, right? And the point of our website is that graphics cards are very fast, and you can now do this on your phone, right? And because we have that easy accessibility in terms of the hardware and in terms of this sort of thing, the major barrier is programming and technical knowledge. And the idea of what we've done is to try and remove that. And the point then is, if we have colleagues in any area of mathematics, in principle, the same idea applies. The same idea of we should be using computers, we should be using interactivity more widely. Okay, let me not ramble philosophically for too long. Let me share this and sort of go through some things. This won't be a very structured talk. This will be a little bit ad hoc and a little bit kind of things that I think are interesting, things that are worth playing with. But I would encourage you to go to this website yourself and click around and play with it. The whole point of this really is that as I'm clicking here, this is solving some equations that give rise to these fun patterns, right? So really at the core of this is some kind of play. Before getting into examples like this, let me start with the way that we normally teach PDEs, or the way that many students first see them. So they have some notion of a function that depends on time and space, and some equation that it solves involving its derivatives. And of course, the first thing we do is not give them much intuition for this, but instead we have them work out complicated formulas and Fourier series and do a bunch of analytical work, which is fine. And I think this is an important part of what we do and teach as mathematicians. But I think it has a disadvantage that some of the students will look at this formula and will have some intuition for what it means and what it does. But most of them, myself included, right? I think I was a fourth-year university student before I had much intuition of why we care about this formula, what this formula tells us. So the sort of first simple thing you can do is you can just plot this formula effectively, or equivalently, you can just solve the equation from first principles, which is what this simulation does. The idea, right, of course, is that this number, this sort of how wiggly the function is, changes how quickly it decays in time, right? That's sort of the moral lesson here, which is maybe not so obvious from the formula. If I run this simulation, so this is solving it with some initial condition, that's some amount of wiggly function, the wiggly function decays in time, and this goes to a flat state. If I change how wiggly the function is, again, as Adam was saying, using sliders or typing things in, so I now have a function which is a lot less wiggly, and it decays in time a lot more slowly, right? Very, very substantially more slowly is it decaying, versus if I breathe there, then it decays very quickly, right? And this is really the lesson that comes out of this sort of separation of variables argument that we often do in first or second year mathematics at university in the UK. An important thing as well is to then start looking at things in higher dimensions and to really think about the intuition of what's going on. So this is I won't go into too much of the physics or too much of the details, particularly for those who don't know PDEs. But this is a model of heat, right? This is a model of temperature moving in space. And it's a lot easier to see if you imagine I set a fire here and I say, well, what happens to the heat? The heat is going to spread out. And as the fire dies, the heat sort of dissipates, but it's dissipating in a kind of spatial way. And allowing someone, to paint an initial condition or to paint a function and then see how this function evolves in time and space is the whole point. I should say that every single simulation on this website is equivalent to every other simulation in the sense that if you start with any of them and you just press buttons by typing in here and changing what the equation is, you can arrive at any other simulation. And anyone can modify these and anyone can play with these. So that's really a big part of what we're doing here. We recently added something where you can change boundaries. So if I have something like a model for temperature, at the moment, I'm saying that the temperature can't leave the space, but I could say that maybe there's a loss of temperature here. So things are sort of being taken away, which is given by, say, a Dirichlet condition. And I could say at this boundary that there's a flux of temperature coming in. And then if I do this, you then see that there's, sorry, this Zoom has a couple of funny tweaks here. There's sort of a flux of temperature coming in. It's sort of diffusing or it's sort of moving in space and leaving out this side. And again, this is a lesson that you can get from purely analytical working it out, but it comes alive in a way, I think, when you can play with it. There are lots of much more complicated lessons that can be taught, particularly ones that are very hard to work with analytically or very hard to teach if you just give demonstrations, but much easier for students to play. So what I will do for maybe 10 minutes is I will show you some of my favorite examples of this and some of the things that I think are really important and really nice lessons. Let me see, there's a few in here. So there are things like Schrodinger equations, things like particles in a box. I won't spend too much time on these because when I give talks, particularly to experts, they will say, well, these are all linear equations. These are all very easy. You're not, doing anything because you can solve them analytically and you can just plot the function as a function of time. More complicated cases are models like this that involve some kind of nonlinearity. And because of this nonlinearity, there's no hope of solving this equation analytically. So there's an important lesson as well in how we teach that there are hard lessons that we sometimes want to teach, but are very hard to write, for instance, exam questions about. So one of my favorites is this model. So this is a model of a population that this has, for people who know differential equations, this has three steady states. It has a steady state at 0, a steady state at this parameter value a, and a steady state at 1. And if I look at the ODE version of this, which I've given in a few recent talks, this represents a population that unless the initial population is above some threshold, the population will die out. So the initial condition of this ODE has to be above this value a, or the population dies out. And if it's above this value a, then the population will go to some carrying capacity. And this has an ecological interpretation in terms of something called an Lie effect. So this is just a sort of phase plane plotter with this model. Sorry, the notation has changed. This is just a thing, a website by Daryl Nestor that I like. And you can see if I'm above here, I've set that parameter to 0.4. If I start on the x-axis is time, on the y-axis is the population, and these integral curves are just solutions of the ODE. It's exactly what I was saying, that if I start above this, I go to this sort of carrying capacity or this positive steady state. And if I start below this, I go to this one where the whole population has become extinct, right? So this is quite important for modeling and ecology and things. But if I think of a PDE, that means I add a term that represents some kind of spatial movement. And it turns out that the dynamics, the behavior of the system can be radically different, and it can be almost impossible to say anything with pen and paper from just the model. But by playing with it, you can get some intuition. So as an example, let me add a color bar to this. Right. So as an example, I've set this parameter a to be 0.3. So we would expect if the initial population is above somewhere over here, that the whole population would grow. Whereas if the initial condition is somewhere over here, the whole population would decay and we would go down to this white state versus this sort of darker blue state. If I click, I've now created a density, an initial, cluster of, say, animals that are above this threshold in the center and then sort of decay away to being below this threshold. And then if I run this in time, the whole population dies out, right? So the lesson is that because of diffusion, the whole population dies out. And that also happens if so let me pause this. If I start with, say, 3 initial conditions that are sort of separated away, but if instead I start with something like this, not quite, maybe something like this, then you get a much more complicated behavior, right? Now the whole population essentially can survive. And this is something where entire monographs and research papers have been written about this model and this kind of problem. And in general, it's very hard to get much intuition for what are the thresholds and what are the sort of mechanisms that allow a population to survive in this case. But if you just play with it, right? If you just sit on your computer and click and sort of play around, you get quite a good intuition. And we've had a decent amount of success trying to teach these, let's say, moral lessons that come out of the modeling by allowing students to play with it rather than trying to just struggle with the sort of pure formal symbolism of these kind of models. It's also useful, so this is a classical model of sort of traveling waves and traveling phenomena, and we always mention examples of this, such as in epidemiology or in ecology, but it's much nicer if you can visualize this in a way, that they can actually see more details and really get some intuition of what's going on. So a famous example of this is the invasion of the grey squirrels into the UK, driving the red squirrels to extinction in most parts of the UK, except for some parts of the Scottish Highlands. And here, because all of this is sort of done in an interactive way, all we've done is we've taken an image of the UK given by this, and we've set the computational domain to just be this image effectively. And then we've solved a model, again, I won't go into the biology too much, but this is a model of competitive exclusion where this population invades. And importantly, we've picked a color scheme where it's clear where the reds are and it's clear where the grays are. Now, of course, the model starts being wrong around this point because you do still have red squirrels here. And there's a nice complicated conversation you can have about accounting for why the reds still persist here. And this sort of thing. But the fact that this is not a square domain, it's not a fictitious sort of mathematically idealized geometry, I think is sometimes helpful to get across to students, because we can only do things with pen and paper when these sort of modeling problems are quite idealized. But the idea here is that the geometry, the sort of complexity of this part of the UK can just be plotted and can just be visualized.
Yeah, so Andrew, there's
Yes.
there's a question in the chat, which is, can we set our own domain? I mean,
oh yes, indeed. So let me find, I don't know. Let's see if I don't know if I have a good example, but what I can do is I can start with the simulation. You can click on this part, and I can change this to be anything I want. That's any kind of indicator function. So this just says solve the equation in the domain given by this indicator function. And if you provide an image, then your image can be anything you want, right? A technical point here is that this approach will only work if the boundary conditions are the same everywhere. So what you cannot do, because partly the UI is very complicated to do it, would be to set different boundary conditions in different parts of the domain. That's the only, let's say, technical caveat here. So if you click on any simulation here, so this is an example of the 1912 Spanish flu spreading throughout the US. If I click on any simulation, so if I just start with this sort of traveling wave one and I click domain and I click custom, this is just the indicator function of a circle, right, given some geometry. And if I change this equation of a circle to be the equation of any two-dimensional shape you'd like, then this will sort of go through. Because this is all done on GPUs, I should also mention that you can do all kinds of interesting things in plotting. So this is an example of, again, not going into the physics, this is an example of something called a beam equation, and then a sort of membrane version of this. For people who know, this is related to Foppel von Karman. So this is, you can think of it as a membrane, but because it's all on a GPU, you can plot this in 2D or 3D as you'd like, right? So I can make this a two-dimensional object, but I can also think of it as a surface. And if this is a membrane that's meant to model plastic deformations, well, then I can click and I can see sort of elastic waves rather, traveling through this membrane. And it's a little bit more interesting, right, being in this sort of three-dimensional geometry. On the non-mathematical front, we've made use of this. I'll get into this a little bit later. We've made use of this in writing stories that are hiding the equations. So these are really shallow water type equations. Here's an example on a circle, right? This is running a sort of traveling wave in a shallow water system, but you can just click and turn this into a three-dimensional simulation and sort of rotate it about and see sort of waves splashing. And we think, at least, that this kind of idea is helpful in really motivating this idea of play and motivating this idea of interactivity. This sort of feature, again, is exactly as Adam said, more or less copied from Desmos, where you can create different views of your simulation. So if you build any simulation you'd like, you can name this and call it whatever you'd like. I can give you a quick example of, say, making your own thing. So this button here is a model of pattern formation. This was the one we started with. So again, if I sort of click, I can get something that forms a pattern. But maybe I don't want to click. Maybe I want to do something like prevent someone from clicking. Maybe I want this to be done on a circle, right? Maybe I want a specific initial condition. So maybe I want a random number as my initial condition. +1, maybe that won't work. Okay, maybe this won't work with this simulation, but I could start with something like this. And then importantly, yes, and I've disabled the brush, of course. Importantly, if I then want to send this to a student and to give this student the simulation that I've made, or a colleague or whoever you'd like, you can press a button to sort of copy this link, right? And once you have this link, you can paste this, and then it will be a copy of exactly the simulation that you've just made. So the whole point of the website really is to allow people to create and to make whatever they'd like. There are some fun things that I can mention briefly before getting back into the sort of more mathsy part. A lot of this started with thinking about art and thinking about visualization in this way. So this is, again, a sort of Turing pattern, which is quite close to my research interests. So this is a system that forms patterns, but it depends on space. So all this is some equations that form patterns, but there's this function here, I sub t, and I sub t is this image here. And if I want, I can just go to Google and I can find, for example, this picture of Adam, maybe.
Can I quickly point out, while you've got this on the screen, these two pictures on the left, right? Right, so clearly there are some years in between these pictures. I went back to the exact wall in Italy to get this updated version of this picture. I was very pleased with myself, and you get to enjoy that as well. Sorry, as you are.
Yes. So right, if I then go to whatever this image is, right, I can then turn Adam into a sort of horrifying Turing pattern. And maybe it looks a bit nicer if I do it this way, right? Okay, maybe it doesn't look a bit nicer, but the point of this whole interactivity and ability to play is that if a student or anyone opens this on their phone and they press this image, it will by default bring up the camera app, right? And they can take a photo of whatever they want and turn it into some simulation of some equations. Again, for the sort of experts, this used to be very hard, or at least this used to always require some level of programming and some level of really playing with it. But the whole idea is that I can change any of these parameters. I can type in anything as a function, right? If I type in something like this.
Yeah, so indeed, Andrew, there was a question in the chat. Can we change the equations, for instance, add some terms on the right-hand side?
Yes, exactly. So you can add anything you want to this. This will probably blow up, but let's just try it anyway.
Ah, right, because there was another question in the chat, which is what happens with numerical instability? Is there a message displayed to say to the user that there is a numerical artifact in the simulation?
Yeah, so here I add a bit of time-dependent forcing, and you can see there's a bit of pulsing. If I make this a bit stronger, this will probably get worse, right? Okay, now we've done something really quite psychedelic, but the point, is indeed you can add whatever you want to this. There's a bunch of documentation here, which I won't bore you with, but you can just sort of type whatever you'd like. I think if I remove this one, I'm going to get a numerical instability because the equation is no longer well posed. Let's see. Oh, maybe I won't. All right, let's see if we can just break it. Make that a 2. Okay, maybe let's not make this time dependent. Just make that a 20. Or let me increase the diffusion coefficient. There we go. So there's the numerical instability. As soon as there's a numerical instability, it will tell you that either your equations are wrong, you've typed in something which is nonsense, which in this case, the equations are fine. What's happened here is that you have to reduce the time step. And this is something where we can't hide this. We can't solve this problem for someone who knows nothing about the numerical solution of PDEs because all of the methods used are what are called explicit. And that means that there's always going to be this issue that if some term in the equation is too big or too small, it can cause certain issues. So here, this is really an instability caused by the time step not being sufficiently small. The advice is to reduce the time step. And in principle, that will always work. In practice, you will hit fundamental limitations. In this case, I can just reduce this number and get something that runs. The disadvantage to doing that is that the actual simulation will now take longer, right, in real time, because it is solving the equations in real time. And so the whole system has to kind of go through this more slowly because I've changed this. So there is always a trade-off here between the speed of what we're visualizing and what's going on in terms of the numerical methods. It doesn't do anything clever. So the user will always have to modify this if they put in something which blows up, or if they type in equations that don't make sense. So a good example is if I go back, something that might be more familiar for people who have played with these, if I go back here, there's a whole bit of analysis which says that this sort of heat flow, this operator, is perfectly fine, and solutions of this equation are very, very well behaved. But if I run the equation backwards in time, it's not well behaved, right? So a backwards heat equation essentially doesn't have any classical solutions, and so our numerical method won't invent a solution. Instead, it will just blow up to infinity, and then we detect this blow up to infinity. Again, there's quite a bit of documentation on this, but as we know, people don't always read documentation. And we've tried to write things in such a way that, particularly given all of the starting examples on the website, you won't have to. So I think Adam and I tend to specialize in mathematical biology, but we've added lots and lots of other examples of other phenomena that we think are somewhat relevant. So there's a bit of fluids on the website that we're expanding a little bit. So this is a sort of Berger's equation. And this is related to things like shock formation. And here we've only done this in one spatial dimension because the sort of physics of shock waves really is, in some sense, understood best in one dimension. When we teach it, it's this way. For any of the simulations, you can just make this a two-dimensional simulation if you want. So Here, the initial condition is given in a one-dimensional way, but I can imagine if I change this initial condition, if I added something like this, okay, that's too much. Let's say, and then maybe 5 times pi, something like this. Then here I have, of course, I have a numerical instability, right? All right, let me not faff with this too much, but you can take any of these simulations and make them one-dimensional or make them two-dimensional. There are lots of things here that are very hard to get a handle on analytically. So this is an example of slime molds and pattern formation in slime molds. We will ask exam questions for students to essentially compute things like this. This is a sort of instability criterion. And this instability criterion says that the system should form a pattern from a sort of Turing type instability. Again, the fun thing is that the system will form a pattern. If I sort of pause it at this point, you say, well, it's sort of turning into stripes and spots, but the system will then evolve in time into a very nice screensaver, right? A sort of very nice active thing, which is no longer given by a simple stationary time-independent function. And this is nice, I think, for students to see, because the things which we can solve, the things which we can get a lot of intuition with pen and paper, are quite limited. So this is especially true in applied mathematics, that most people doing research in modeling or this sort of thing are quite well aware that more complicated models will give really quite a rich diversity of phenomena, but it's hard to ask questions about that on a 3-hour exam, for example. And so we don't always show the students that there's really a sort of zoo of all kinds of interesting things to explore. So part of at least our goal here is to give them a better taste for this and a better sense for sort of exploring the phenomena. So I'm not going to go through every example. I won't show you too many more things, but I just want to sort of point at a couple of things that we've made.
There's a nice question here in the chat, Andrew, which is, can we save the results and maybe later on use them in another software like MATLAB?
Yes. So there are a few caveats. So one caveat is if you're doing what I would call serious science, you would not want to use this because the numerical errors are quite large. They're large in a quantitative sense. So qualitatively, the phenomena does a decent job of is captured reasonably well. Even things like that bifurcation threshold are captured within, say, 5% or less of the real threshold. As I said, you can save a particular simulation with a given initial condition. So even if I change, say, the initial condition or boundary condition or any of this, copying this link will save that simulation exactly. You can also pause it at any point, and you can save an image, and then this will then download an image of the simulation at a particular point. If you're doing things where you care about, say, the final time that the simulation has gone to, you can say, we'll only run it for this many times, or up to this point in time, and you can plot what the current time is. So if I look in the bottom right, it's now plotted, it's now saying what the current time is, and I can say we'll stop at, let's say 200, and then it will stop at 200, and then I can say export an image. You can also save a video, so you can record an animation. If I start, say, from this clip, this will then record a video, and then I click here to end the video, and it will give you, importantly, a link to frequently asked questions in terms of video for things like social media, messaging. There are some details here about encoding videos depending on what operating system and what browser you're using. When we describe this, we always say that there's actually nothing clever on the very technical numerical analysis side, but there's been an enormous amount of work to get the user interface to look nice and to do things like this that will work on Android, iPhone, tablet. It currently does not work on my wife's Amazon Fire television, but with that exception, we've had good success of getting all of this to run reasonably on other devices. So I would be a little cautious of using this for data analysis, but you can do some things. So I do currently have a final year, or sorry, a master's project where the student is generating patterns in the software, they're saving images, and they're doing spectral analysis, Fourier transforms and things on these images, and that works reasonably well. I wouldn't necessarily do that for a research paper because I'd want slightly better convergence. Quite a lot of the arithmetic that underlies this is done using single precision arithmetic. So there are quantitative questions. You know, are you really capturing quantitatively what's going on? But as long as you're happy with qualitative analysis, really, I would say anything in teaching, anything in demonstrating, we think that the accuracy is good enough. As I was saying, if I take any simulation, I can plot it in a different way. So this is plotting a model of vegetation, and you can do it in a sort of more three-dimensional way.
Yeah, so in terms of using the data, I think in terms of using this for research, it's not really the forum so much for research use of this. Our sort of impression is that this is better than you think it should be.
Yeah.
And in terms of taking the simulation and then getting it coded up in MATLAB or something. So we're working on a project at the moment. So come back next year and we will tell you how well that's gone. But we understand that, and in fact, so Andrew, you can say something about this, but in terms of using this as a tool for research, just like playing around, right? You know, students are people who play. Then knowing that you can also do the same thing or a lot of the same thing in a slightly more rigorous way using a software where you can play around with precision is a sort of a side project that we're working on.
Yeah, I can mention very briefly, very selfishly, I wrote a paper that I more or less only discovered by the phenomena, which I won't go into here, but I more or less discovered this phenomena by playing around, by typing in my own equations, by clicking, and then going and checking that this was a real phenomenon. We think that there's a lot of potential for that, and there's a lot of potential of getting students to be much closer to research level things. Again, on this previous page, you know, this is quite a recent 2023 paper, a very hardcore analysis paper by a colleague of ours, Dan Hill. And in fact, Dan went and in his paper includes these sort of localized solutions, and he used this website as a way of just sort of initially visualizing them, initially getting a picture. So we think that one big advantage of this is bringing students or bringing anyone up to speed relatively quickly with quite modern research in different areas, and really being able to sort of see this stuff quite quickly. I should mention there are a ton of features. There are a ton of other things I've not talked about. I don't think I want to belabor too much. There are a few things that I've showed you a little bit. You can take any of these simulations and you can overlay things like a vector field. So I could take, for example, the gradient of this function and treat this as a vector field, and I'm hoping that this will just plot. So I've now plotted the gradient of the solution, and then this itself will evolve in time and space. So this sort of vector field coming off of the solution of this PDE, if I start it again, right, you can then see how this vector field evolves as you're solving this equation. You can do things like plot a time series. So for example, if I wanted to know what is the total mass of some chemical concentration in some model, then this will automatically plot the integral, right, or the total mass. Okay, I've not normalized by the area, but plot something that is the integral of this function. We're still tweaking the UI. We think it's always hard that as you add features and you add buttons and things to press, right, it's very easy to overwhelm someone. So we sort of are trying to add things and make things more complicated, but at the same time wanting to make sure that people can actually use this and can actually play around. And there's quite a lot of difficulty there, let's say.
We've got another good question in the chat. Do we get students to submit work using this? How much are students playing with it? And can we set some problems where the students can use some kind of theory to predict what kind of results they would get? for example, give them a picture and then ask them to find the parameters that we use.
So let me show you all my email. There's a very nice colleague of ours, Adriana Dawes, who has sent some problem sheets. So we use this a little bit in our own teaching. But we have a colleague in the US who's been using exactly this software to have students. I think she's done a better job than I have, right? So in our course, I ask a couple of questions where the students can optionally go to this website and play around. But in this colleague's class, she's at Ohio State. She actually asks the students, right, choose an equation from this section of the textbook, run it in this software, make 3 distinct changes, provide a link to each of the simulations, and write a paragraph on the effect of these changes, engage with one of the stories, find a journal article. So we think that there's a tremendous opportunity to really use this in teaching. One way of submitting things is to say, provide a link, right? So if a student goes and they discover something or they develop something, they can just send you a link back. And these links seem to be reasonably robust. The only disadvantage to these links is that they are quite long. So you'll notice this URL kind of explodes. But the point is not to be human readable. The point is just to get a link to exactly the thing being studied. I have a little bit of trouble. So I was trained in the US, and this person, Adriana Dawes, is in an American university where quite a lot of the coursework in this university is summative, but is coursework. So she can do things like this, like say, provide a link, and this counts as part of the student's summative mark. So particularly in Durham, we're very exam heavy. So it's been hard for me to encourage the students to use this too much, only because I know that when they go to sit down for a 3-hour exam, I can only ask so many questions that will be related to an interactive tool. So there's a bit of that. We use a bit of that here in Durham, but we're changing to hopefully provide a little bit more coursework during the year, and then these sort of opportunities will occur. So there were a few, there are quite a few questions. So this colleague has really been trying to push it in her course, and we're using this as an example of what we might do. One thing that we're developing at the moment, which doesn't exist yet, is to take the textbook that she's using, which is Evan's PDE book, and to make an index of simulations for Evan's PDE book, so that you can find essentially most of the topics in this book in a sort of visualized and interactive way. In terms of submitting work, indeed, there are links. We have a markdown parser here, which we've used for colleagues and other things. Of course, you're welcome to use this as well. And the idea is that someone can say, I have a question about this equation, or I don't know anything about this, or I can't get a simulation here to work. They can do things like post a link like this, and then this will update here. So we're toying with the idea of, do we teach our students a bit of Markdown or a bit of the LaTeX that's within Markdown, and have them actually submit things that look like this that include links. So at the moment, we've not done what I would call a sophisticated use of the tech. That said, we've had really good response, even purely for visualizations and demonstrations. Right, I'm trying to think, Adam, have I missed anything crucial?
No, I don't think so. So how long has this been live for now?
About a year. So we posted it officially April of last year.
Right. So it's so this is some software that's or the website that Andrew and I and our colleague at UCL, Ben Walker, wrote. Ben did a lot of the heavy lifting. And so if you are interested in the code, it's available on GitHub, so it's all open source. Yeah. That information is available, I think, on the about thing. Yeah. So you can go and, if you're curious, you can go and see how it all works. Something that we're quite proud of here is, so we have some analytics on sort of visitors, so when they come to use it. So it's sort of doing all right. We're getting a couple of hundred people a day, so that's nice. Something that is particularly pleasing is that we're seeing them when people come to visit the site, that they're sticking around for sort of 4 minutes on average, which is really high, right? So people are coming and they're actually playing. So that's been a nice stat, because you can share this on something like the math subreddit, right? And Reddit will like it because it's got pretty pictures and that's all nice, and they'll come and they'll never come again. But what we're hoping is that people will continue to come back to it as they find it increasingly useful. Ah, yes. Okay, Andrew will enjoy showing you this.
So the very last thing I'll show you is that it turns out when you discretize a PDE, what you are effectively doing is building a cellular automata. So we're constantly adding examples and we're constantly doing things. And particularly Ben Walker does a tremendous amount of the back end. And so I have an idea and I force him to do work that I feel very bad about. But we had the idea that since you are effectively solving a cellular automata, why can't you just use exactly this interface to do something like Conway's Game of Life? So as of last week, we've now implemented Conway's Game of Life, and we're hoping to actually develop this a little bit into doing other types of cellular automata. So this is currently on our testing server. This hasn't been pushed to the live site yet. But the main point here is that we are constantly developing new things. We're constantly adding new examples. We're very interested if people want support for teaching, or if people want support, they have a good idea, they can email us. You can send us your equations if you're having any trouble getting anything implemented. If you think of other applications or other things that we can do with this. I'll speak in Glasgow in a few weeks at something Colette Mayer is organizing, and I'll talk about the advantages and disadvantages from the accessibility point of view and the inclusivity point of view for software like this. I think that's all that we wanted to say. I think.
Yeah, it's so we're really curious to see how people use it. If you find it useful, you're more than welcome to always suggest things that you think would improve the site. Basically, we're constantly working on it and taking on sort of community feedback to make it useful to you.
Okay, well, thank you very much. People can show their appreciation by using the reaction buttons if they would like. Right, we're coming up to time, but there might be chance. I mean, you've been answering questions throughout, but there might be a chance that to answer a few more questions if people want to put it. They've not been putting in the Q&A, and they've mainly been putting it in the chat. But
Sorry, I broke the paradigm, Kevin. Sorry.
Well, that's all right. No, it worked perfectly well. That's you've got through all the questions, but I believe so. Has anybody got any more questions? Please put them in the.
I was going to say, while people are typing, so it's all hosted on GitHub, the website itself, right? And the simulation is solved on your device. So it's not being processed by a server. So it's this means that you can guarantee that the website is going to be working. Or if the website is down, Microsoft is down. So like it's a bigger problem. So if it's something you're interested in, it should be nice and stable.
Right. Good. Okay. Looks to me that there aren't any more questions. I mean, I had a number of questions, but they all got answered along the way. So, but I think the main takeaway from this is that it's a fantastic thing to play with. I've played with it a bit, and I'm hoping to use it in some things. I might be in touch with you about that. But if people do want to contribute, I mean, I think particularly about the teaching, I think it would be interesting to see what people do with this. They can just send the stuff to you. You'll somehow collate it on your website, perhaps. Is that?
Yeah. So we haven't decided what exactly how we'll do this. But if someone sends us a really interesting example, for example, we will absolutely just post that. At some point, we are hoping to develop more integrated things like lecture notes. So you can take any simulation and turn it into an iframe and put this into HTML lecture notes.
Yeah. So this is a key point. So exactly, if you think there's a simulation on here, or if you can create, because the simulations are easy to create for whatever system it is that you want to simulate, right? You can type it in just directly onto the website because you can customize all the equations, right? And then you can export that as an iframe. And as Andrew says, you can put it into you can put it on your website. You can put it, if your lecture notes are HTML based, then you can just put it directly in as an iframe. And so in that way, you can sort of do it yourself. But also, if you've got an example that's particularly nice and would be nice to share on the main site, then yeah, please let us know.
Okay, great, fantastic. So I think we're going to draw it to close there. Thank you very, very much.